So the next speaker is well known to the SU2 community. It's Toby. He will tell us about Unsteady CHT Adjoints and optimization. Thank you, Toby.
Right. Welcome. So first, I will start with a little motivation, introduction, and then do a very brief primary modeling section in that we create the nomenclature for going into the discrete adjoint method. So I think the first part you have already seen multiple times now, but maybe the extension to unsteady multi-zone. Maybe you've seen the two parts alone, right? But maybe not the combination. And then I will showcase a small application, a very easy test case because computational requirements are pretty high. So unfortunately, I was not able to do a really big there. And then I close with a short time. So, of course, as we've also seen today, many problems are not only unsteady, but they are also covering multiple physical disciplines. And on the right, I have kind of the broad aim where my work started, which is a infinite exchanger with a solid ethereal block, cooling electric going through it. And of course, we can think that when defining an objective function, we can find a better shape which optimizes an objective function, which might be temperature on this lower solid surface, for example. And to do this kind of shape optimization, we are very lucky that we can employ adjoint-based methods to get the gradients required for that shape optimization. And consequently, of course, like with these two observations in general of these two needs, my aim is to enable the shape optimization for unsteady CHT using the discrete adjoint method. And to set the nomenclature, so unfortunately, I'm not able to showcase in the application this infinite exchanger I was showing before. I have to resort to the most simple case, which is a 2D pin in crossflow. So a very simple mesh to start with, like 22K or 28 if you take both zones cells. So pretty small case. I will denote the vector of all grid node coordinates by X. And then the solution to the PDE is governed by this fixed point operation or operator, fixed point operation. And the operator for the fixed point duration we call G. That's also, I think, nomenclature which we often use in the SU2 community. And we iterate that until we, of course, can drop the duration index here, and we just have a true statement that the solution to the PD problem U is equal to the solution of this fixed point iteration. And this fixed point iteration, fixed point operator is dependent on the solution, which is, of course, like something like temperature, velocities, or just temperature on the mesh. And in the following, we will also see that this fixed point operator, the dependency, it changes when we have multiple zones and or multiple time steps. Finally, we are interested, of course, in a scalar objective function, which we will call J. And what we want to do the gradient-based optimization is the derivative of J with respect to the mesh state X. So we're interested in dj dx. And that's all the requirement we need for this point to jump right into the discrete adjoint method. And I have to bother you with the, steady state single zone derivation, which maybe some of you have already seen before. So the 2D constraint optimization problem is we want to minimize over the mesh our objective function. And we have this constraint that we want to version the space of valid solutions to our Navier-Stokes equations. And we're going to approach that. So we want, at the end of the day, we want, as I said, dj dx. So we transform this constraint optimization problem into an unconstrained by forming the Lagrangian, introducing the Lagrange multipliers, which later I will refer also to the adjoint variables. And then we take the total derivative with respect to the mesh state X. And because we added 0 we know that L is J, and that's then also true for the derivative. And so if we want to know our shape derivative, dj dx, we can compute this formula here on the right. And we want to avoid computing du dx, because u represents the final solution. So taking a derivative with respect to u would mean that we have to kind of get iteration through the whole iteration process with multiple nonlinear iterations. So what we can do is we require this partial L partial U, which is the multiplication factor, to be 0. And we can do that by choosing the adjoint solution state lambda such that this is actually true. And when we evaluate that formula, we will arrive at what is often referred to as the adjoint equation, which in itself is, again, a fixed point iteration scheme. Once we have that, we go back to this equation on the bottom left. This whole second term drops, and we're left with computing the LDX. And if we evaluate the LDX, this is our formula where we need the adjoint solution state, and we have our final derivative. And to highlight how that's visible, what is the work we need to do, first we need to solve our primal problem, then we need to solve our adjoint problem, and then finding this final derivative that's fairly cheap in comparison to those both steps. And now I will directly jump to the unsteady multi-zone derivation. And here we especially see that this fixed point operator is now dependent on a few more things than just one solution state vector u. So now it's basically the same. We follow the same recipe, but everything gets a little bit more convoluted. But at the end of the day, I think it's rather simple. So our objective function is now a dual sum over multiple zones. So like we have fluid zone and a solid zone and multiple time steps, right? And we call each contribution like Fn. N we use for the time step index and M for the zone index. And then our fixed point, which we have to solve in the primal problem, we have to solve that in each zone. So we have to find a solution in the fluid zone and in the solid zone, and all of that over multiple time steps. And we're using dual time stepping second order here. So in this fixed point G and M, so the fixed point operator in time step N for zone M, we're dependent on both UN, which is the sum of all, which is the collection of all solution state of all zones in that very time step N. But we're also dependent on not both U, which is just the solution of the prior time step in the same zone N. And I've not collected all the possible solution states here, because when we reformulate that a little bit, we see that every zone is only dependent on another zone in the very same time step. So this, if we look at that formula, we have a set of partial derivatives which will be 0 at the end of the day. And so we again put up the Lagrangian. It's the very same task we have to follow. So take the derivative of the Lagrangian L with respect to all solution states UN, UM, and set that to 0 and evaluate. And when we do that, we see that this first two terms, these are the ones we know from our steady state single zone evaluation, and these two new blocks appear. And if we were to do just unsteady single zone, for example, we would just get these terms additionally. And if we would to do steady state multi-zone, we would just get these additional terms. And now the property I've shown here earlier that leads to the circumstance that by combining unsteady simulations and multi-zone simulations, we do not add any more terms, which is quite nice, because once you've done unsteady adjoint and multi-zone adjoints, you can rather easily combine those two. Now with that we have the derivation. I want to quickly showcase my application case. So as I said earlier, it's a very simple vortex shedding in laminar flow at Reynolds number 100. And The optimization problem I set up is I want to minimize surface time average temperature on the inner pin and constrain the aerodynamic drag on the outer pin surface to not exceed the value of the initial design. And unfortunately, the animation, I think it's not playing, but that's fine. I think you all have seen vortex shedding before. And to quickly showcase the FFD box setup, so I've submerged the outer pin. So I'm only moving the outer pin in an FFD box with 18 points. And if I click this a little bit back and forth, I think also most of you have seen the working wise of an FFD box. But this is a fairly restricted setup, also simply to be able to actually manually look at different design variables and not get swamped with thousands of design variables. And I've put a pretty drastic limit on the deformation because you can quickly go into invalid mesh states and degrading meshes. So it was pretty strict there. And on the same setup, so these design variables, they directly correlate to these numbers. So I did a gradient validation because before doing an optimization, I first have to know, is my gradient actually exact? And in this plot, we see the objective function for temperature and a plot over all design variables with the discrete adjoint gradient in red and the fine turbulence gradient in this striped version. And the first in the same for drag below. And the first instinct is, yeah, that looks pretty good, but how good is it actually? So I've picked just design variable number 4 now for average temperature here, the first two numbers. And this is something like 1/1,000,000% in relative difference. And the red numbers here are non-matching digits. For drag, it's a fairly similar result. And across all design variables, we get similar result, although most of them are a little bit worse. But overall, I think we can say we have a pretty good match. And going to the optimization, which I can now finally do. On this top left plot, we have the design iterations here on the x-axis, and in red, the optimization history in temperature, and in blue, the constraint of drag. And we see it's a little bit choppy of an optimization, but the SU2 optimizer, which I simply use from SciPy, made a good job at the end of the day, keeping the constraints kind of in balance and optimizing the objective function. And I've only drawn line segments whenever two consecutive valid designs were chosen. And on the bottom, the gradient norm is not really that interesting, but we also see that, for example, from iteration 40 on, it stops computing gradients. And when we look at the shades, I have here a series of shades. So it's kind of morphing into this constraint optimized design. And on the right, I have also the drag optimized and the temperature optimized without any constraint. So we can see that constraining the drag, if we think of the optimization of temperature, kind of acts to some extent as a volume or surface area constraint. So that would be also an interesting case to just try with a geometrical constraint. Also in the shape, unfortunately, the animation is not playing, but you really see that the main reason or the main case here is that the separation point is quite delayed backwards in the optimized design, while basically ducking down in the front. So the overall projected surface against the fluid stays the same, so it keeps the drag constant, but this overflown surface grows, so that is optimizing the temperature. And this brings me to my end. So we've seen the extension, the gradient validation. We can apply this to the full design chain, and all of that is already available since version 7.3.1. And all of the setups you've seen is also available. So I'm happy to everyone like checking it out or giving it a spin. And now, thank you for your attention.
Thank you, Tom. The floor is open for questions. Anyone?
What is the ramp cost of doing unsteady multi-zone adjoint, like in comparative stuff in, let's say, equivalent problem in steady state and equivalent problem in unsteady, how expensive is it?
If you repeat for the
Yeah. Nitish is asking for the general cost comparison when going to unsteady multi-zone. So I guess multiple things come together, especially also the unsteady solver for incompressible flows is quite a lot less efficient than the compressible one in SU2 at the moment. And also for CHT, I think, one can explore other methods like more strongly coupled, but the weakly coupled approach we currently have. So at the optimization, you're looking at, I don't know, 4 days. But I've also converged like the primal and adjoint quite a lot. But especially when going to single zone fluids, in this case, we're talking about, I don't know, a couple of minutes. If you couple it, it already grows. And if you compute an adjoint for that, I think for me, the factor was something like 3 or 4 that the cost grew. But it was also because I was very conservative with linear solver options, iterations I gave it to really, be able to show an optimization that comes to kind of an end. Because I saw that if I relax it, I often get into states where like the prime of the adjoint doesn't converge anymore. And then you can, get in the process, but I wanted to be automated. Yeah. But yeah, not feasible for really bigger simulations at the moment, unfortunately.
And is the test case available already on the test cases? Or
I think it's not merged into the test cases yet. I have a repository on my own, but I will merge it through.
thank you.
Josh.
Yes, what is the latest feature of the larger problem?
Well, I mean, performance is the name of the game here, right? Depending on where you want to get it, so you can get it in the algorithms. You can get it so basically changing to, for example, strongly coupled CHD or other approaches for the unsteady time stepping. I have no definitive answer for that, but sorry.
It's a string. There's a whole list of things you could do.
Yeah, I mean, if you can just like put down raw compute power, you can do it. It just takes you a second or more.
So yes, it'd be nice to put down that as a roadmap. At least the people who are interested can work on that roadmap and try to get more else. Considering you know the most about it, I look at you.
Sure, I can put down some recommendations without any guarantees of success. Well, unfortunately, I don't have like this magic bulb. Okay, cool.
Are there other questions? Maybe I have one for you, Tom. My road is often because I work a lot with applications and I have contacts with industries to formulate interesting problems, not knowing a thing about how to solve them. Here, what is very relevant is the coupling of design optimization to 3D printing, right, for heat exchangers. In the aerospace industry, this is very relevant. One of the interesting aspects of this coupling is the fact that for very expensive heat exchangers, which need very costly materials, it would be, and that's probably a bit far-fetched, but interesting to optimize the fluid dynamic performance with a manufacturing process by which you can venerate the metal with 3D printing to minimize the cost. Can you imagine a path forward in that direction? It's a multidisciplinary optimization problem.
It sounds pretty much like you lengthen your design variables, right? Oh, I think we lost power again. Or
Oh no. Please don't.
Or maybe nobody moved the mouse. I don't know. But essentially, in addition to the mesh, you would just also add like material properties, like densities, and then you have to be clever on straightness. Sorry?
And constrain them because one of the problems is that several less costly materials cannot resist high temperatures. So
that then becomes very interesting. And then you need to be a little bit careful about how to, I guess, blend between two materials, because probably difficult to have, like probably easier to just have like a copper core and then in an aluminum shell, but you do not have like a linear switch between the two materials. So you have to be clever about how to switch between like some, I don't know, some curve or some heavy side function, which is a little bit smooth. I don't know. But I think the level set guys from topology optimization there are doing that already a little bit. So
thank you very much, Tom.
Okay.